We're supposed to have two speakers today in person, but unfortunately the second speaker had a cancellation flight, so she will give her talk from remote. And the two speakers of today will provide an appetizer for the LEM workshop, which many of you might be aware will is scheduled for the other days of this week. So the first speaker is Ryan Pfeifle. Ryan is a NASA postdoctoral fellow at the NASA Goddard Space Flight Center, where he works with Kimberly Weaver in the X-ray lab. So he obtained his PhD from George Mason University in the spring of 2022, a bit less than a year ago. As for the science interest, Ryan is working on obscure AGN growth and the search for and understanding of dual AGNs across the merger sequence. He routinely combines X-ray observation from Chandra XMM New Star with diagnostics in the mid-infrared, optical, and radio to study the often elusive population of dual AGNs. Ryan has led also works focused on the search for dual AGNs in the mid-infrared selected mergers, multi-wavelength effort combining first triple AGN in the late stage merger, and also new mid-infrared diagnostics of AGN obscuration. What else can I add? And he's also a member of the AGN working group for HIPX, HEXP, and last reminder, usual reminder for the Zoom people that we are going to record this, as you might have seen already. So if you don't want to appear in the video, this will be the right time to switch off. Ryan is going to talk to us today about seeking out elusive giants, multi-wavelength searches for dual AGNs in the local universe. And with that, Ryan, thanks for coming. For yours.
Thank you. So, appetizer for LEM. This is not LEM focused, so sorry for the shocker there. So thank you so much for that introduction. I'm very excited to be here. Thank you for having me. I'm going to break this up into basically three chunks. I'll give you a brief overview of selection methodologies for dual AGNs and the selection methodologies we use in my group, and talk a bit about our new star observations of mid-infrared selected late-stage galaxy mergers. And then I'll launch into the second part, which is looking at type 1 dual AGN candidates and how fiber spillover effects led to that misclassification. And then I'll finish off with a brief discussion, qualitative discussion of the first literature complete multi-AGN catalog that I've been assembling. So I'm going to see if I can get this to work. I'm going to skip over the controversial part about whether mergers are important for triggering AGNs and just sort of launch right into it. So we know from simulations that galaxy mergers induce tidal torques that can then induce radial inflows of gas into the nuclei of the galaxies, placing that gas in the vicinity of the supermassive black holes, which can then possibly accrete and light up as AGNs. And this is some wonderful work from Phil Hopkins's group. And so simulations also show us that in these galaxy mergers that you can get more correlated AGN growth in the latest, typically in the latest stages of the galaxy mergers. So around 10 kiloparsecs or so, you start to have correlated AGN activity, so you get your dual AGN phase. And so this is something that's probably an important growth phase, but I'm going to talk about the selection methodologies and then circle back to more theory side. So early discoveries of dual AGNs were serendipitous. They were typically, you spotted them at X-ray observations or on the radio. These are prototypical examples of dual AGNs from the literature. But the first selection methodology that was really used on a large scale with the SDSS was selecting based on double-peaked O3 lines. And so this is an example from Liu 2010 showing a dual AGN with distinct narrow line regions. And indeed, some of these double-peaked AGNs do show signs of being dual AGNs. But the majority of them are not. And less than 15% of double-peaked AGNs are duals. Most of them are driven by radio, jet, and cloud interactions, accretion disk physics, et cetera. Now, another common method is BPT spectroscopic emission line ratios. This is from Liu 2011, where they looked for pairs of galaxies that showed Seifert liner or composite ratios. So these blue points and the circles are what they selected here. But the problem with BPT line ratios is that you can get light spillover between close fibers, Shocked gas can give you liner and composite ratios. Post-AGP stars can contaminate these ratios. And obscuration can also dilute or hide your AGN signatures. So the optical is not always as clear-cut as we'd like it to be. Hard X-ray selection is pretty clean. When you look at the BAT AGNs, those that have companions within 15 kiloparsecs, you have 50% of those are duals. And 20% of those confirmed with the X-rays, you don't see in the optical. So this is confirming that point before, that you need to combine multiple wavelengths to start finding these more readily. And you actually see, as a function of decreasing pair separation, you have an increase of dual AGN systems found using hard X-ray selection. Now, circling back to the theory, these are simulations from Laura Blecka's work in 2018, showing a mock UGZ images of a gas-rich major merger there. And on the right-hand side here, I have the bolometric luminosities, the column densities, and the Wise colors. This is combined Wise colors for the system. And so what you'll see is that the A, B, C, D points correspond to the panels here. This is the late stage merger, and that your bolometric luminosities and your column densities peak in the late stage mergers going into post stage mergers. And you have these incredibly red Wise colors, high column densities. And so what you expect in these late stage mergers is heavily obscured AGNs that are growing rapidly, and they should be intensely red in the mid infrared. And this is all in line with what we know about merger-induced AGNs. You have higher fractions of obscured AGNs in mergers than in control galaxies. And we also find higher fractions of Compton-thick AGNs in the late-stage mergers than in the early-stage mergers. So what we did a couple of years ago now, we took a sample of mid-infrared selected galaxy mergers, and we followed up with Chandra to look for X-ray point sources. And so what we found in 2017 and in 2019 was that a substantial fraction of this 15 merger sample, 8 out of 15, show these dual X-ray sources indicative of dual AGNs. Now, when you compare the X-ray emission to the mid-infrared emission, these systems are X-ray suppressed, heavily so, which implies that they are heavily obscured AGNs with high column densities. One interesting discovery that came out of this program was that we actually found the first confirmed triple AGN. So this is J0849. So 3 X-ray point sources coincident with the nuclei, heavily obscured column density along the central line of sight towards the central nucleus, and 3 BPT AGNs. And this was confirmed by us as well as Lu 2019. So really exciting discovery. But if we're looking for not only mid-infrared selected dual AGNs, but also looking to see if they're heavily obscured, the next step we want to do is look at NuSTAR. So this is work we're currently doing. So we've selected a subsample of these galaxies to look at with NuSTAR to try to constrain their column densities. 7 of these have NuSTAR observations. And 3 of them were published previously. So the first one was the triple AGN we published previously, but then NGC 4922 and Markarian 463. These were published previously as well by Rigi 2017, and then Bianchi 2008 and Yamada 2018. These are all heavily obscured to Compton-thick AGNs. So this is exactly what we'd expect from the NuSTAR observations. In our new paper, we've looked at the remaining 4, 3 of which are not detected. So I'm going to talk about those first. So for those 3, we can only get flux upper limits. We built sets of attenuation curves to try to indirectly infer the column density along the line of sight. So we basically compared the observed 10 to 24 keV flux to that that we expected from the mid-infrared. And so then we inferred the column densities. So these are heavily Compton-thick AGNs if they are due to obscuration alone, if the non-detection is due to obscuration alone. But Chandra provided better constraints on the 2 to 10 keV flux. So what's going on? So here, and these are the NuSTAR observations, by the way. This is 3 to 10, this is 10 to 24, and this is 3 to 24 keV. And that's the full sample of 7. The ones here are the ones in green boxes, which I guess is a little hard to see. This one, and the top 2. So I guess I could use my cursor, shouldn't I? Yeah, that's probably better than jumping, right? This one, and this one. So if you look on the bottom right here, how am I doing that time? Probably running out of time. Bottom right here is showing the observed 2 to 10 keV flux as a function of your 12 micron emission. In black, I plotted the SwiftBAT sample, full SwiftBAT sample with the column densities on the auxiliary axis. The dashed line is what you'd expect for an unobscured AGN. Dotted line is what you'd expect for a heavily obscured AGN. In blue is our full Chandra sample, and in orange is our NuSTAR observations, or the inverted triangles of the upper limits. So new star is sitting squarely above the Chandra observations. So what we think is happening is that Chandra still implied that you were heavily obscured because they're heavily X-ray suppressed relative to the mid-infrared, because they're sitting far off this relation. So we think that it could be a combination of heavy obscuration as well as the high new star background, and that's why we've missed these things in the new star imaging. For the one that we've observed, we actually find it strongly detected in XMM and new star. High column densities along the line of sight. We fit two similar but different models here. One using the Boris model from Bolokovich 2019, and one using the Petrov model, where the difference is just how you're accounting for the reflection in the spectrum. And so we find, again, heavily obscured AGN. We find evidence for two thermal components in the soft X-rays. This looks like a bit of a mess down here. This is just the model if you're interested in what it looked like an X-spec. So again, in line with this heavy obscuration. If you look here, if you're trying to figure this out, basically it's Boris or Petrov. You can swap one or the other out in the model. Bit confusing, I'm sorry. It made more sense at 1 o'clock last night. So one caveat, though, is that the system may not actually comprise a dual AGN. Ford 2020 looked at this and said it's likely a single AGN, so there's that caveat there. How am I doing on time? Because this says 21 minutes, but I don't think I've been going that long. Oh, okay, all right. So, so that's our new star observations. That should be submitted hopefully tonight or tomorrow. Actually, we have the full paper ready. So this is now the second part of the talk. I'm going to jump from mid-infrared selection, sort of, to optical observations. So this is the messy nature of fiber spectra, star quasar pairs masquerading as dual type 1 AGNs. So I talked a lot about major mergers, but I didn't really talk about minor mergers. But minor mergers are just as important, if not more important, than major mergers. So minor mergers tend to become more major across the merger sequence. On the right top, you can see the mass ratios relative to the initial mass ratio. You can take a 1:4 or 1:6 mass ratio merger and grow it to 1:2 or 1:3 by the end of the merger sequence. The secondary black holes can grow by a factor of 2 to 8 in mass. This is shown in the bottom right panel here, where the red line is the secondary black hole with mass relative to the initial mass. And minor mergers are expected to trigger dual AGNs, and they do. There are several examples in the literature, if I get this to work, of dual AGNs found in minor mergers. But these are type 1 AGNs, so they're obscured pairs. We have no local examples of type 1s, especially not in minor mergers. In an unrelated study, looking at mid-infrared selected AGNs, this is the crossover here, we found this unusual system where there were two SDSS fibers, one at the central nucleus and one offset in the galaxy. The central nucleus has this nice set of broad and narrow emission lines. The secondary has a strong stellar continuum, very narrow O3, but a broad N2H alpha complex. And so we said, okay, that's funny. So we went back to the SDSS. We looked to see if there were other objects like this one. And indeed there is this other object, 1713. Again, same thing, strong stellar continuum, narrow O3, broad H alpha N2 in the secondary fiber, but the primary is squarely a type 1-ish. I can't tell you what the exact number is, but it's type 1-ish AGN. And so we went and we looked at the SDSS spectrum. In 1421, the first object, the broad lines were squarely detected at greater than 3 sigma. And in the secondary object, they were actually marginally detected, 0.5 sigma, not great. So that's implying that maybe there's a misclassification in the SDSS pipeline. But regardless, we wanted to follow both of these up. And so when you look at the full width half max values of the broad lines, they were actually different at roughly the 3 sigma level. So that was implying that we're looking at two kinematically distinct broadline regions. So we said, okay, let's follow up with LBT and see if this is a real dual AGN or if we're looking at a case where we have atmospheric seeing conditions that are smearing the emission out to large radii. So we look at LBT, we get our spectra here. You can see the primary continuum very clearly. You have your nice bright emission lines, you have some extended emission, possibly outflows, but mostly featureless secondary continua. So we look at the 1D spectra, no lines in 1713, and much weaker lines in 1421. And the nail in the coffin, rest frame, in our rest frame, stellar absorption features, calcium triplet, sodium D, calcium HK. So what we're actually seeing is not two background AGNs, we're seeing a background AGN and a foreground star conic projection that we just couldn't tell what it was. So Huesman 2020 came up with this nice toy model for atmospheric seeing and fiber spillover issues, which they showed this was a problem for type 2s, but did not have a type 1 in their sample. So if you compare the flux of the primary nucleus to the flux of the secondary nucleus in any of your lines, O3, H alpha, they sit squarely along these tracks as a function of aperture offset. They sit squarely along these tracks where you expect fiber spillover to give rise to these emission features. So essentially, SDSS was just taken in two pore conditions, and you're smearing the emission from the primary out to the secondary fiber's position. So the conclusions for this paper, and this was just accepted a week and a half ago, so it's now in archive if you want to go look at it. We had two candidate type 1 systems, but these are quasar star pairs. Fiber spillover was to blame for this misclassification. Now these results imply that fiber spillover is more common than type 1 pairs because these were the only ones we could find in SDSS that were convincing enough to follow up. But to date, there's no local Z type 1 dual AGNs. And I realize now that I talked about minor mergers, but didn't tell you why I talked about that. These were both minor mergers. So, or would have been minor mergers based on what SDSS told us. And they were dramatically minor by like 1 to 7, and the other one was 1 to 30. So it would have been pretty fantastic if these had been dual type 1s. But we really do need more simulations looking at minor mergers, especially obscuration and gas absorption and dust obscuration. So yay, another paper. So I probably am running up on time here. So I'm going to just finish talking about the Washington multi-AGN catalog. That is excuse me, the goal is to be the first complete literature catalog of multi-AGN systems. First complete catalog of multi-AGN systems from the literature. And so this is supposed to include all dual or so-called binary quasars and candidates, dual AGNs, binary AGNs, recoiling AGNs, and every candidate system. This plot is from an early data release that was internal to USNO only. Now, the hope is that this will have a broad scientific impact. So it's a full accounting of the dual AGN literature. This allows for a targeted multi-wavelength approach for current and future facilities, along with collaborations across multiple institutions. So what you can expect in this release is a huge amount of information for the source catalog. So this comprises over 500 papers from the literature. It's expected to be complete this May. And so this gives you every bit of information you could possibly need to look these objects up. Their coordinates, redshifts, parent names, counterpart names, brightness measurements, all of your ADS and DOI information, additional notes. It's all in an ADS repository that's private now, but it will be made public when the catalog is released. And so our hope is that this catalog will sort of help to steer the field forward and provide information of where we have gaps in research and also how we can make the field more uniform. And so one qualitative aspect here is that the dual AGN field, as I have found, is not uniform and not well documented. So all these lists here, which looks like a lot, and it is, are all the aliases you have to search in ADS to find all these papers. And even when you use all these, you don't find all the papers because every group uses different terminologies, different acronyms. This is like 2 weeks worth of searching ADS in 2020. And so you get over 1,000 papers with all these. You have to sift through all the theoretical and the observational works, figure out what's relevant. It's a whole mess. So this will be the first proper collation of the literature and should make it easier for us to go forward, and will hopefully help us to choose more common terminology so we don't have to search 54 different aliases in ADS. But like I said, this catalog is it's in the works, should be done by May. If you're interested in getting involved with the development of it, or if you have someone you know that would like to be involved, please shoot me an email. I'm happy to bring people on board during the development phase. And we do expect to have multi-wavelength counterpart catalogs looking at near and mid-infrared, the X-rays, radio, so on and so forth. So with that, I'm going to finish up. I think I'm just at time. So thank you so much for listening. I have just 3 things listed here. I have recently published a NuSTAR paper on bulbous galaxies. This is the fiber spillover paper I talked about. And then this is the NuSTAR dual AGN paper that should be submitted by tonight or tomorrow. So thank you so much for listening and having me here. And I'm happy to take any questions you have. Thank you.
Were any questions from the personal people?
So could you comment more on why you use NuStar instead of just Google AGN?
Yeah. So we used NuStar primarily because we wanted to. We had Chandra observations, but they didn't really provide great constraints for the column densities. And we know when you combine NuStar with previous softer X-ray telescopes, you can get pretty dramatic changes in column density estimations. So our goal here was to try to better constrain the column densities, not only in these well-detected systems, but in what we hoped to do was constrain them in these systems, which we were not able to do. But that was really the goal, was to get better constraints in the column densities. Even though with these NuStar observations, the sources would be convolved because of the lower angular resolution. But you could still get a general picture of what the line of sight column density is for the system itself.
When you showed your map of the Washington sample, it looked like there were very few below declination, like stage 5, a good chunk along the equatorial. That one, yeah.
Yeah.
Based on having seen the full distribution of all your data, what are the biases that we have so far in finding the binary AGN?
Yeah. So this is where I have to admit, I didn't have enough time to get an updated version of this plot. So I think this is about 100 papers worth, and there's 500 papers. So this is way out of date. This is from a long time ago, but it's the only thing I had. But in terms of biases, so a lot of the sample is comprised of optically selected sources. The vast majority of them are selected based on PPT line ratios. So any biases you have there as far as contamination from the post-HEB star populations or shock-driven emission that's going to give you liners or composites, that's a problem there. We haven't done as much work with mid-infrared selection. Hard X-ray selection with BAT is really the only clean X-ray selection strategy that's been out, because most of the X-ray papers that come out start from optical selection. So we need other places to start from for selection other than optical, because really when you look at the literature, the vast majority of dual AGN literature starts from the optical and then goes either to the mid-infrared or the X-rays or the radio. And really we need to start from the other wavelengths and work backwards instead. So there's that. So there's a ton of biases. And of course, when I say complete, what does that mean? It's as statistically complete as literature is, which it's not at all. And that's really where following these systems up with more wavelengths and finding new selection strategies will help to fill in those completion gaps. So, yeah.
The large number of them at the equator, that's from Sloan.
Yeah, I believe most of these. Yeah, this is Hitomi 2006. So Hitomi 2006 is the clustered quasar catalog, and so I selected everything below pairs with 100 kiloparsecs or less there. So those are known quasars from SDSS.
For these obscure AGNs, do we have a sense of on what spatial scale that obscuration is located?
That is a great question. I'm glad you asked that. So LoRa's simulations, we go back here really quick. LoRa's simulations, wow, this is far back. LoRa simulations only get down to a resolution of 80 parsecs. So below 80 parsecs, we have no idea what this looks like. I mean, this is really 80 parsecs puts you about halfway into the galaxy. It puts you at larger scales that it's not really the torus anymore, but it's also not really the circumnuclear disk. So this is really showing a lot of the galactic obscuration and not really even the torus. So the torus could be even more obscured than this. And my bet is that it's probably true, especially because she only gets up to about 2e to the 24. I bet you that the torus is probably just as obscured or maybe even more. So.
Thank you. Any other questions from people? Yeah. Okay, so let's thank Ryan again.
Thank you so much.
Okay, and now we'll try to move to the second speaker. Okay, let me stop sharing. Okay. Irina, do you want to try to share the screen?
Yes. All right, you should see it now.
I'm just. Can I dismiss all reminders?
Yeah. It should be muted otherwise.
Okay, thank you. Okay. Sorry about your flight cancellation.
I'm sorry for not being there.
You'll be here tomorrow. Okay, so all right. So no, in fact, wait, what should I do now? Because
The box at the top. You get full screen.
this one here.
Green.
Okay, perfect. Thanks. Okay, so let's move now to the second speaker. I hope to pronounce correctly the name, Irina Zhuravleva. She's currently Claire Booth Luce Assistant Professor at the Department of Astronomy at Astrophysics University of Chicago. She got her PhD at the Ludwig-Maximilian University in Bavaria, in Munich, in Germany, under the advice of Rashid Sunayev. She was then postdoctoral researcher at the Max Planck Institute for Astrophysics in Germany, and also postdoctoral researcher at the KIPAC in Stanford, and also research associate scientist therein. Her talk today is about the physics of the ICM in the new era of high-resolution X-ray spectroscopy. Thank you so much, Irina, and the floor is yours.
Thank you very much for a nice introduction and invitation to give a talk again. I apologize that I cannot be there in person, sudden change in flights. So when I was thinking what to present today, I want to share so many things, but then I decided to focus on perhaps the most exciting thing that will be happening in X-ray astronomy this year. And this is the launch of the new X-ray satellite called X-ray Imaging and Spectroscopy Mission, or XRISM for short. So I'm sure many of you have heard that it will provide high-resolution X-ray spectra of many diffuse extragalactic sources pretty much for the first time. And this is very exciting. So as a member of, as a participating scientist for this collaboration, I was involved in the development of scientific program for the first 6 months of observations. And together with a group of other great scientists, we were mainly focusing on extragalactic diffuse emissions. So basically clusters of galaxies, groups, and massive galaxies. So today I decided to share this program with you to talk a little bit more about what kind of questions we will try to answer during the first 6 months performance verification phase of the satellite, what objects we'll observe, and then at the end of the talk, if I have enough time, I will also focus on more challenging things that we'll be able to do, maybe not during the PV phase, but later, but certainly exciting. So this is a conceptual image of XRISM, how it would look like in the sky. And this is a real image of XRISM satellite. So it was taken in May last year. So it's in Tsukuba Center in Japan, right before the testing started. Right now, testing is complete. Satellite looks healthy. Everything is on track. And it is ready to be moved to the launching facility in Tanegashima Space Center in Japan. So we are planning to launch it in May, May, maybe late spring, let's say, right, 2023, on a Japanese H2A rocket. All right. So, and on board there will be 2 instruments. The first one is Resolve, which is X-ray microcalorimeter. It will provide non-dispersive spectra with energy resolution about 5 to 7 electron volts, hopefully closer to 5, maybe even lower, in a standard bandpath in X-rays, right, from 0.3 to 12 keV. It will have a field of view about 3 arc-minutes and angular resolution 1.7 arc-minute half-power diameter. So just to give you an idea, what will be the improvement for those who haven't seen Hitomi results, I'm showing the spectrum over here. So Hitomi had resolution about 4.6 EV. So we are aiming to reach similar spectral capabilities with XRISM. And the red curve over here shows a spectrum from CCD. So improvement is just dramatic. I don't even need to comment on this. So we'll resolve individual lines, measure the line broadening shifts, intensities. So all the metallicity studies and gas kinematic studies will be finally open for the community. The second instrument is Extend. This is an array of 4 CCD detectors, and the key feature here is that it will have very large field of view, about 38 arc-minutes on a side. All right, also exciting. So what are the key science objectives? They are listed here on the slides. To summarize in one sentence, we'll be looking at transport and circulation of matter and energy on the universe, both on large scales that are important for understanding structure formation, and going all the way down to the vicinities of the black holes where we have pretty extreme conditions, and we'll be basically looking at circulation of energies there as well. And of course, since it will be for the first time, we'll have such kind of data, we're all hopeful to have new unexpected science there. So this looks pretty exciting too. All right, so I will focus on clusters of galaxies in my talk and what we plan to do during the first 6 months of the mission. So just a quick reminder, you know that clusters of galaxies are the largest objects in the universe. They are found in the cosmic web, basically in the intersection of the cosmic web filaments. And this movie just shows what is happening inside these massive dark matter halos. These are numerical simulations from illustrious TNG simulations. So you see that there is constant accretion of matter along the filaments, and then there are also occasional violent mergers, right? So major mergers, or even small and kind of continuous small-scale mergers. So these are extremely dynamic environments, and even we need to understand the kinematics of the gas, and we need to understand how energy is basically transported during these processes. So these are one of the largest problems in understanding large-scale structure evolution, and this will be able to probe with CRISM. So besides this large-scale phenomena, we know that in the center of many galaxy clusters, there are strong AGNs, there are supermassive black holes that are releasing energy into ambient gas, right? And thanks to the presence of this hot gas in clusters and groups, we are able to trace, basically all this AGN feedback is imprinted on X-ray images, right? And here I show a famous example of AGN feedback in the core of a Perseus cluster, and you see central AGN, you see cavities, which we know are filled with relativistic plasma that is injected by jets. This relativistic plasma is pushing the hot gas. That's why these cavities are created. And we can easily detect multiple generations of these cavities. Besides that, there are shocks, there are outflows, inflows of the gas, sound waves, internal waves, turbulence. So there is a lot in these central regions, and they're also extremely dynamic. And understanding kinematics, simply even measuring like kinetic energy in gas motions, looking at metallicity, looking at different mixing processes is a key in understanding all this AGN feedback, which is again one of the major problems in galaxy evolution theory. So that's just a reminder. Let's go directly to the program, what we plan to observe. Right, so let me start with the closest galaxy cluster to us, which is Virgo, and the Virgo cluster, and it's also very bright in X-rays. So just a reminder how it looks in the background. I show a Chandra image of the central region of M87. So this region is completely dominated by AGN feedback physics, and since it's so nearby, we can even resolve jets and see small cavities, resolve shocks, see this prominent filamentary structures, which also we believe is related to the AGN feedback physics. So with CRISM, we propose these 4 pointings. Altogether, we will spend about 500 kiloseconds as the highest priority, maybe additional 100 kiloseconds as a lower priority. And the goal here is to basically spatially and spectrally resolve AGN feedback region. Right, so in the central region, we will basically probe turbulence very close to the jet itself. In the eastern pointing, we will aim to basically look at gas kinematics in the cold phase and compare it with the hot phase. So we'll try to basically do multi-temperature, multi-velocity feed to the spectrum. And just to illustrate you that we can do it, I show this simulated spectrum in the middle panel, where black shows the spectrum, how we would see it with proposed exposure, and the best fitting model. And the 2 different components for hot and cold gas are shown with purple and orange curves. So we'll be able to do this for the first time, multi-temperature, multi-velocity feeds to the spectra. So it looks exciting. Then in the northwestern pointing, it's actually looking relaxed, but it's not that relaxed. There is a shock front just going across this pointing, and our goal is to look at the turbulence pre and post shock here. So we'll be able to basically split our pointing into 2 parts and extract spectrum from both. And this southwest pointing will try to basically do very similar analysis like in the eastern arm, and to confirm that what we find in eastern arm is consistent also with another one. To summarize, so looks exciting. We'll be basically looking at mixes of kinematical mixes and metallicity mixes in this AGN-dominated region. And in terms of metallicity, I don't think I mentioned, but we'll be able to measure metallicity with a statistical uncertainty of about 5 to 7% only, right? So this looks really exciting. So the second object that we'll be observing during the PV phase, this is also a large program for CRISM. This is, of course, Perseus cluster, which is, the brightest cluster in X-rays, as you know. Hitomi already observed this cluster, but only central region. So the sign squares over here, the three, these are actually Hitomi pointings. So we'll try to build on and expand our observational program of Perseus, right? An idea is to have these measurements, these 4 pointings in one radial direction. Right, so we'll point in the center. This is a region heavily dominated by AGN feedback physics, and we'll verify what Hitomi has measured and basically measure turbulence driven by AGN feedback. In the C1 region, here we will also be within region dominated by feedback, but we also know that there is a kind of cavity, a rising bubble, and we also want to look at the motions which could be generated in the wake of the rising bubble. There are some tentative interesting results coming from Hitomi, so we want to confirm them. The outer 2 pointings basically will be showing us gas kinematic, which is dominated by mergers rather than feedback, at least based on our current understanding. And ideally, we want to have this radial profile of measured velocities and see what are the features. Right now, we don't have a single model that could realistically model that. So that will be exciting to see this transition from regions dominated by feedback to regions dominated by mergers. Between these 2 outer pointings, M1 and O1, there is also cold front. So we will be able to look at shear motions produced by the cold front. So in this M1 pointing, for example. Besides that, we know that there is a pretty strong mini radio halo in the center of the Perseus cluster, and these black contours show this radio halo. And one of the exciting things would be just to test turbulent reacceleration of cosmic ray electrons. And the way we can do that, we can basically try to search for a correlation between the strength of the radio power or like efficiency of radio power production versus kinetic energy in the gas. And if there is any strong correlation, that would give us a strong support for the turbulent reacceleration. So besides dynamics, we will also look at metallicity, and we will get radial profiles of metallicity that will allow us to put very tight constraints on enrichment mechanisms. So statistical uncertainty will be here of about even better than in Virgo, like about 1, 2, 3%, just few percent only, based on our estimates. And besides these metallicity studies, we'll be also able to detect very rare elements, at least in the central 2 pointings. So what else we can do? So the central pointing, there is also a presence of cold gas. We know there is a famous picture in H alpha that shows a lot of beautiful filaments. So this is basically optical image of the central pointing, how it looks like. So we know that there is some fraction of a cold gas, and it will be extremely interesting to look at interactions between this cold gas and hot gas through charge exchange process, right? So I'll talk more about this in the next slide, but with the central pointing, especially if we get this additional 200 kiloseconds, right here, we'll be able to do this interesting physics. All right, so the next object is elliptical galaxy NGC 4636. So we propose the central pointing with 100 kiloseconds in total. And this is also region dominated by feedback. So again, science goals are very similar, right? Looking at metallicity and looking at velocities. And the goal is here, the idea is kind of combine the studies of all these 3 objects and try to get some insights about AGN feedback physics as a function of radio halo mass, right? So Perseus will be the most massive object, then Virgo, and of course, NGC 4636. Of course, we will not answer all the questions, but it will be exciting to see the first indications of maybe feedback is kind of changing phase from being more gentle in massive halos and more kind of aggressive, more in a low mass halos. All right, so what's next? We will observe also Centaurus cluster. So we propose to have this red pointing, basically a central offset pointing with 250 kiloseconds. And the goal here is to measure these kind of strange metallicity patterns that we measured so far with current X-ray observatories. So we know that in the central part, there is a very strong drop in metallicity as predicted from, for example, Jeremy Sanders standards and others. And it is unclear whether this is a result of our kind of limiting data. So there are a lot of temperature components and they bias our abundance measurements, or there is actually depletion of metals. So with CRISM, we'll be able to resolve this problem, hopefully. And the outer part of the same pointing basically corresponds to this peak in metallicity. So we detected here enormously high metallicity, about 1.5 even, which is pretty strange. So we'll be also verifying what's going on in metallicity, and of course, trying to find models of enrichment that would explain observational data. So we will also measure turbulence in region dominated by AGN feedback. So there is also pretty strong feedback over there. But in contrast to other objects that I just showed, here AGN is relatively quiet. So it would be sort of interesting to compare this radio quiet AGN regime compared, to other more actively more active AGNs. All right, so now let's switch to other type of clusters where we don't have strong AGN feedback, but we know that they're undergoing through some mergers. So we will look at the Como cluster, which is the brightest nearby emerging cluster, and we proposed central pointing observation about 200 kiloseconds. And the goal here is basically probe turbulence about motions driven by mergers, right? We know there is no AGN feedback. And given that it has relatively flat surface brightness here, we expect that turbulence will be isotropic, and we'll try to probe basically textbook example of turbulence in the ICM. Hopefully, we will have enough time for priority B pointings, and in particular, we want to observe 2 out of 4 these offset pointings and about 100 kiloseconds per pointing. With that, we'll be able to look at actually structure function of turbulence, right, and try to put constraints on injection or energy dominated scale, which will be very exciting. This is something we'll be doing directly for the first time. What else? So the next emerging cluster is Able 3667. Probably many of you also know this cluster. It's very famous. This is an example where we have a merger, and there is a very prominent cold front that was detected with Chandra. Right? So this is a Chandra image of Able 3667. This is a famous prominent cold front over here. And we use this cluster to measure the sharpness of this cold front that could directly be used to constrain microphysics transport processes, viscosity and conduction in the ICM. So the challenge right now is that there are a lot of degeneracies in this analysis, which are partially coming from the uncertainty of the merger geometry. So there are 2 options over here. First of all, this cold front could be created by the sloshing of the gas, or this could be a stripping situation when we basically have a subcluster going through the main cluster and we have a strip tail behind. Which basically model is applicable to Able 3667 right now, we don't know, but measuring velocities, especially inside the cold front, could reveal, could give us the answer, because in one case we expect that there will be strong turbulence along the line of sight, in the other case we not expect it based on simulations. So we propose to have this inner observation about 180 kiloseconds inside the cold front to basically measure velocities of gas motions, to reveal the merger geometry, and basically directly constrain gas viscosity and conduction in ICM. So that will be kind of opening door to interesting plasma physics, microphysics of ICM. Finally, we will be also looking at Able 2029. This is actually one of the most relaxed cluster and also very bright, observed with current observatories, right? And the goal for this object would be to measure velocities all the way to R2500. So these are distances which are particularly interesting for cluster cosmology, and try to measure again velocities, non-thermal pressure, and see how our mass measurements through hydrostatic equilibrium are biased, right? And we propose to basically have these 3 vertical pointings over here from the center all the way to R2500. The simulated spectrum, as you can see in the middle panel, is shown in black. So we are requesting exposure about 320 kiloseconds. And the reason why we actually need to do multiple pointings along the radius and not just pointing there is because the instrument has very large point spread function. And in order to estimate correctly what is the contribution of light from the central region in these outer pointings, we need to have short observations to be able to basically decompose different contribution from different spatial regions, right? And this figure just shows in color different components to the main spectrum, again, from the same regions. So here we want to do cluster cosmology, and probably with this radial information, we'll be also able to measure velocity structure function. All right, so this is how the program looks like, quite ambitious, but looks very exciting and very promising. So in the rest of the time, I wanted to say a few words about some more challenging sort of new exciting physics that we might be able to do, hopefully during the PV phase, but for sure even after PV phase with additional observations. So first process we want to detect is a charge exchange. As I mentioned, in the inner regions of many clusters, we have cold gas, we see very strong H-alpha emission, and inevitably this cold gas could interact with the hot gas, right? Again, I show image of a Perseus cluster, X-rays on the background, black and white, and H-alpha emission is shown with the color. Hitomi actually already revealed that there could be some interesting features that show like kind of weak indications of this charge exchange. So in particular, this feature over here at energies about 8.6 keV shows some indication about 2.4 sigma detection of anomalously high flux, which in the transition that expected from charge exchange. And another feature is, for example, here, it's 1.6 sigma excess only. So with new additional observations, especially if we manage to combine them with direct Hitomi measurements, we'll be able to robustly establish this new interesting physical process that we're not able to detect in ICM so far. Another interesting effect is resonant scattering, right? So just a reminder, we know that clusters are in general optically thin, so the photons propagating freely. We don't need to worry about any radiative transfer effects. However, some photons at the energies of a strong resonant line could have non-negligible optical depth. And as a result of that, they could undergo multiple scatterings before reaching line of sight, right? So as a result of this effect, we may expect that the fluxes of the strongest lines could be suppressed. And in fact, if we do radiative transfer simulations, for example, for the inner region of a Perseus cluster, we see that the original spectrum optically thin that is shown in orange, basically the flux in the strongest line is significantly suppressed if we take into account resonant scattering, which is shown in red. And actually, Hitomi confirmed that this effect is present in the ICM. So if you look at the central region of the Perseus cluster and we measure the ratio of the W to Z lines in the helium-like iron triplet, we find that the measured value was actually significantly lower than the predicted one from the optically thin plasma that is shown with the colors here. So that was the first direct evidence that resonant scattering is present. So the same effect, will be present in many, many other targets, including PV targets. So we need to be very careful when we are modeling this high-resolution spectra, because the strongest lines could be quite significantly affected. So why do we care about this resonant scattering, except for the fact that we need to be careful when we model X-ray data? Well, it actually provides us an independent way of measuring velocities, right? So the idea is that resonant scattering, the probability of the scattering also depends on velocity. So the stronger are the velocities of the gas, the lower is the probability of a scattering. In other words, the closer our spectrum would be to the optically thin case. Right. So, and if we measure line ratios and we do tailored radiative transfer simulations, we can infer independently velocity, like it will be complementary to the Doppler broadening studies. Now you may ask, why do we need this? It sounds complicated. If we have Doppler broadening, why do we need to care about this? Well, for a number of reasons. So the reason number one is that we know that resonant scattering is mostly sensitive to small scale motions along the line of sight. So you can imagine a situation that if we have our line of sight and if there are like bulk velocities, as a superposition of these bulk velocities, the line could be broadened, right? However, resonant scattering will not be affected. So we will not see basically any effect there. So comparing both resonant scattering and Doppler broadening, we can say something about the scale of motions along the line of sight, which is very valuable information and crucial for correct interpretation of the data. Moreover, we showed that radiant scattering is also very sensitive to anisotropy of motions. So the effect will be different if most of the motions are radial or tangential. And it will not only change the amplitude effect, but will also affect the shape of the line itself. And if we have very nice and highly exposed, spectra, we can start to detect all of this, right? So it looks exciting. So again, what Hitomi measured in the core of the Perseus cluster in terms of velocities, we basically obtained velocity probability functions as shown here in red. And you see that the peak velocity was about 150 kilometers per second with rather large statistical uncertainties, right? And within these uncertainties, we were consistent with direct measurements from the Doppler broadening. So once we have CRISM in space, hopefully we'll be able to reduce these uncertainties significantly and start doing it all this kind of additional kind of non-obvious diagnostics of the velocity fields. Right, so I mean, I can probably skip this slide. So basically it is shown resonant scattering that we were doing using RGS data on XMM Newton. So we were able to extract high resolution spectra from the compact cores of many elliptical galaxies and apply the same technique and basically measure velocities in a sample of bright nearby elliptical galaxies. So we see velocities are about 100 kilometers per second, or Mach numbers are about 1.5. So it will be great to verify all of this with a CRISM, right? So one of the problems with RGS is that our spectra are convolved with a special extent of the source. With CRISM, we're not going to have this problem. And of course, with CRISM, we'll be able also to look at larger regions. So on one side, we'll be verifying this data. On the other side, it will be extremely complementing to our measurements. So that would be exciting. Finally, in the last few minutes, hopefully I have them, I wanted to measure velocity structure functions and velocity power spectra. So having measured velocity amplitude is great and it's important and it is the first step. But ideally, we want to measure velocities as a function of spatial scale and look at cascade of turbulence or in general gas motions, because this will allow us to directly measure amount of energy that is dissipated, and looking at the slope of a spectra, we can also probe interest in microphysics. So far, we were mainly measuring velocity power spectra indirectly using high resolution imaging data from Chandra. And the idea of the method is shown here. I'm not going to talk too much in details, but basically it's related to this very simple relation between the amplitude of density fluctuations that we measure directly from X-ray images and velocity. There is proportionality coefficient that we calibrate with cosmological simulations. Again, happy to answer questions if there are any. I will just quickly skip it. So, but applying this method into the central bright regions of Kuku clusters, where we have strong AGN feedback as well, basically gives us prediction of expected velocity power spectra that are shown over here. And we do see that the typical velocities are about 100-300 kilometers per second on scales of 100 kiloparsecs or so. Interestingly, this is consistent with what Hitomi measured in the core of a Perseus cluster, right? That gives us promise, but in order to actually test it properly, we need to measure velocity power spectra directly using high resolution spectrum. Right. And another interesting comment is here that even that measured velocities are relatively small, we showed before that actually if all these velocities dissipate, they may actually provide a lot of energy that can stop vigorous star formation in regions dominated by AGN feedback. So this turbulence could be actually important process in all this AGN feedback story. And again, directly measuring this would make significant push forward in our understanding of physics of AGN feedback. So basically verifying this scaling, verifying this method will be very important with CRISM. Another thing why we want to measure power spectra is we want to measure basically dynamical coupling between hot and cold phases. So I already showed this H alpha emission maps from the clusters, some of the clusters, and with this data we are actually able to measure velocity structure functions, and the pixels are extremely tiny here, and colors show basically measured velocities. So very recently, together with Yuan Li, we measured actually velocity structure functions, and the results are shown on these figures below. And if we are able to measure similar velocity structures, but on a hot gas phase, that would be extremely interesting to basically compare these two different gas phases and see if we are kind of they are following each other. Another exciting part here is that with this cold phase gas, we are able to reach special scales that are very, very small, and I don't think we'll be able to reach with Hitomi or any other X-ray mission, at least in the near future. So, generally, these cold gas observations could provide us additional insights into ICM physics. But first, we need to verify this very commonly used assumption about dynamical coupling of hot and cold gas phases. So I don't think I have much time left to talk about specifics, how we measure velocity, structure, function, but just to say a few words, the basic idea, one of the basic ideas is basically to look at velocity dispersion as a function of radius. And the idea is that if we have a cool core clusters with very peaked emissivity towards the center, then if our line of sight goes through the center, most of the photons will be coming from the innermost bright region. If we go at some projected distance, this region will be larger, right? Simply because surface brightness is dropping. So if we measure velocity dispersion as a function of radius, we are basically looking at velocities as a function of scale, right? And it is easy to do some simulations to show how this velocity dispersion, which is shown here in black, will be following or not following structure function, and sort of they are following each other pretty well. Right, so this is one of the ideas that could be applicable to cool core clusters like Perseus or Able 2029. For coma-like cluster where we don't have this peaked emissivity, we actually derive a pretty simple analytical expression between the power spectra in 2D and 3D and how they're related to structure function. And I'm not going too much in detail, but you can have a look at, for example, John Suhon's paper from back to 2016, where he basically performed specific predictions for this coma cluster. All right, so that's all what I wanted to cover today. So the takeaway message is that CRISM is exciting. It will open a new era of high-resolution X-ray spectroscopy very, very soon on timescales of a few months. Our program, initial program, will be exciting, and we'll try to touch on different aspects of ICM physics. But of course, after the first 6 months, the guest observer program will start, and we will be looking for exciting science coming from the community. This will be just the beginning, in my personal opinion, of high-resolution X-ray spectroscopy, that we will be mainly focusing on the brightest parts within clusters and galaxies, but future missions such like line emission mapper, for example, will be absolutely exciting, because it will be doing high-resolution X-ray spectroscopy beyond these bright regions and focusing at the cluster outskirts where surface brightness is very low, focusing on cosmic filaments, and actually study these hot halos around regular galaxies, more like Milky Way size of galaxies. So all the exciting science, the way how I see it, like all the exciting science that we're doing right now in hot halos and clusters, hopefully we'll be able to do on scales of regular galaxies. But not going to talk more about line emission mapper. You will hear a lot about this mission and these workshops this week. So I will stop here, and I'm happy to take questions. Thank you.
Thank you so much. You have any question from in person, people? Online? No, yeah, probably we are right on the ending time. Just a reminder, you can take advantage of the many time slots available for the appointments. So Irina is not going to be here tomorrow morning because she's flying, right, Irina? Okay.
Right.
So,
yeah.
we should be able to change the Google spreadsheet for the appointments. So maybe tomorrow afternoon is still okay, and maybe also Wednesday. So please have a look at the spreadsheet. So, and with that, I think we are all done for today. I will see you next week, usual day, usual time, usual place. Thank you. Thanks, Irina.
Thank you very much. Yeah.
And have a good trip.